If you look up at the night sky, you're likely to see a few dozen stars, maybe the Milky Way if it isn't too cloudy. But what you're actually seeing are the pinpricks of light from other galaxies, each containing hundreds of billions of stars. Those galaxies aren't just out there, though. They're moving around. Astronomers have mapped these motions, and they show that everything around us is streaming along with the flow of the universe, expanding away from each other. In other words, the more distant a galaxy is, the faster it appears to recede. This discovery in the 1920s led to the birth of modern cosmology. But in the 1970s, astronomers found something strange. When they looked at galaxies close to us, like those in our local group, they saw that they were all moving together as a group toward a certain direction. But that direction was a mystery. It was hidden from view behind the center of our galaxy, where dust clouds blocked our telescope's view. But they could map the velocities of these galaxies and extrapolate their paths. And what they found was disturbing. All the galaxies in our local group, including the Milky Way, were hurtling toward a mysterious region of space with an enormous gravitational pull. The strange region was dubbed the Great Attractor. It turned out that the Great Attractor wasn't just a random quirk of our neighborhood. Most galaxies in the nearby universe seemed to be drawn towards similar regions, forming a sort of cosmic current. These currents guided the galaxies along fixed paths through the larger expanse of the universe. By tracing these paths, astronomers built a map of the large-scale structure of the universe, revealing a network of galaxy clusters and superclusters connected by these rivers of galaxies. This network is known as the Cosmic Web. But the Great Attractor remained a mystery for decades. It was until the early 1980s that astronomers were finally able to map the distribution of galaxies within 300 million light-years of Earth. They found that the Great Attractor was not a single region, but a whole cluster of galaxies. It was essentially a gigantic whirlpool made of hundreds of galaxy clusters, some of which were large enough to be seen with the naked eye. But even after this discovery, astronomers struggled to explain why the Milky Way and its galactic neighbors were being pulled toward this cosmic whirlpool. One team claimed that a supermassive black hole at the center of the Virgo cluster was responsible, and that its gravity extended far beyond the cluster itself, reaching out like a cosmic spiderweb to capture wayward galaxies. Others argued that the culprit was even more massive, a gigantic cloud of dark matter that permeated the void between the galaxy clusters. But the truth turned out to be more mundane. In the late 1990s, a team of astronomers used data from the Hubble Space Telescope to map the distribution of galaxies over a much larger area. They found that the Great Attractor was simply a part of an even larger structure, a supercluster of galaxies known as the Laniakea. So why did the galaxies in the local group appear to be hurtling toward a relatively minor structure like the Great Attractor? It was like watching a river flow toward a small puddle, when there was an entire ocean just beyond. The reason turned out to be that the universe wasn't just expanding, it was also accelerating. As the universe expanded, the pull of gravity between galaxies grew weaker. Eventually, the force of expansion overcame the force of gravity, and the galaxies began to drift apart. But because the expansion was accelerating, the effect was stronger the further out you went. Galaxies near us seemed to fall toward the Great Attractor because we were closer to it. But as we continued to accelerate, we would soon pass beyond the Great Attractor and find ourselves speeding along another river of galaxies toward the even larger ocean of the Laniakea Supercluster. In other words, we're not falling into the Great Attractor, simply being carried along the cosmic current along with all the other galaxies in our local group. This discovery revealed the true nature of the universe. It wasn't just a random collection of galaxies. It was a vast, interconnected web, the Cosmic Web. Yet, despite this progress, astronomers still had more questions than answers. What was the Laniakea Supercluster like? How big was it? And how many other superclusters were there out there? Or were there even larger structures that united all of the superclusters into a single cosmic web? What were the immense rivers of galaxies really like? To answer these questions, astronomers needed a much wider view of the universe. But that was easier said than done. Mapping the positions of thousands of galaxies across billions of light-years was a monumental task. It required the combined efforts of dozens of observatories around the world. But in the 2000s, technology finally caught up with theory, and astronomers were able to assemble the first map of the entire cosmic web. It revealed a universe more vast and intricate than anyone had ever imagined. The Laniakea Supercluster turned out to be nearly 500 million light-years across, containing hundreds of smaller galaxy clusters and groups. And beyond it, astronomers saw other superclusters, each one more massive than the last. Some were shaped like filaments, others formed vast sheets that spanned billions of light-years. And connecting them all were the rivers of galaxies, streams of hundreds of millions of galaxies coursing through the cosmic web. As we continue to explore the web, we're discovering even more fascinating structures, such as the Hercules Corona Borealis Great Wall, a gigantic wall of galaxies nearly 10 billion light-years across. It is the largest structure ever discovered in the universe. But the most exciting discovery is that the cosmic web is not static. Like the rivers of galaxies that flow through it, the web itself is flowing, driven by the mysterious force of dark energy. This discovery has led to a new understanding of the fate of the universe. As dark energy continues to accelerate, the flow of the web will become faster and faster, carrying the galaxies away from each other until every star in the night sky goes out, leaving us in total darkness. All of which goes to show that the more we learn about the universe, the more mysterious it becomes. The Great Attractor. Some sources refer to this phenomenon as the Great Attractor, while others say the Great Attractor. So which is it? Is it Great Attractor or the Great Attractor? While some style guides may have a preference, there's no definitive rule. And since the name was coined by astronomers themselves, without any special style guide, they've used both versions interchangeably. It seems that even the Great Attractor itself can't make up its mind. So for the sake of linguistic flexibility, we will go with the former. Also, please don't get too hung up on this. There are far greater mysteries at play. Now let's dive deep into the heart of our galactic neighborhood, exploring the strange and fascinating features of this invisible gravitational behemoth. First, we need to understand some foundational events that set the stage for our cosmic mystery. Foundational events. The universe began with the Big Bang. From this unimaginably hot and dense state, space expanded rapidly and matter cooled, forming the seeds of galaxies. This period of rapid expansion lasted until about 380,000 years after the Big Bang, when the universe was still opaque. As photons streamed freely through the cosmos, bumping off free electrons, the universe had been filled with a faint glow from the Big Bang. This ancient light, now stretched by the expansion of the universe, is what we know today as the cosmic microwave background radiation. It's the universe's baby picture. It reveals tiny temperature variations barely a degree across the entire sky. These tiny fluctuations in temperature correspond to variations in density, with peaks marking where galaxies would eventually form. Expansion of the universe. In the early 20th century, astronomers like Edwin Hubble made a groundbreaking discovery. When they measured the light from distant galaxies, they found that almost all of them were redshifted. Their light stretched toward longer wavelengths. This was evidence that galaxies are moving away from us. The conclusion was revolutionary. The universe is expanding. Its expansion isn't like galaxies flying apart through empty space. Instead, it is space itself that is stretching. On the largest scales, the universe is not static, but dynamic. With galaxies carried along in the cosmic expansion, like raisins in rising bread, but this expansion is not the whole story. Superimposed on top of the universal expansion are local motions, what astronomers call peculiar velocities. These are deviations from the smooth Hubble flow caused by the gravitational pull of matter. If one region of the universe has a higher density of galaxies and dark matter, its extra gravity tugs on nearby galaxies, drawing them in. Over cosmic time, this creates flows of galaxies, where vast regions move together like currents in an ocean. The Milky Way, for example, should simply be carried outward with cosmic expansion. But instead, measurements show that it is moving at over 600 kilometers per second relative to the cosmic microwave background, the oldest light in the universe. Something is tugging on us. Galaxy clustering. Galaxies are not sprinkled randomly through space. They form groups, clusters, and superclusters, interconnected by filaments of dark matter in what cosmologists call the cosmic web. This vast three-dimensional structure emerged from tiny initial variations in the early universe. Over billions of years, gravity has sculpted these variations, pulling matter together to form the grand cosmic tapestry we observe today. Understanding the distribution of galaxies is crucial to unraveling the mystery of the Great Attractor. Galaxy groups. Small associations, like our local group, containing a few dozen galaxies. Clusters. Larger gatherings, like the Virgo cluster, containing hundreds or thousands of galaxies. Superclusters. Even grander structures, stretching across hundreds of millions of light-years, linking many clusters together. These structures do not sit still. They pull on one another, warping the flow of galaxies across the universe. The Shapley Supercluster, home to the Great Attractor, is one such structure. Peculiar velocities. We're not merely cruising through an empty universe. Our cosmic voyage is steered by unseen hands, the gravitational pull of matter distributed across the universe. This force, known as peculiar velocity, influences how galaxies move beyond the universal expansion. For instance, our Milky Way, along with other galaxies in the local supercluster, is drawn towards a massive, invisible entity known as the Great Attractor. This gravitational anomaly, hidden behind the plane of our galaxy, exerts a powerful influence on our cosmic neighborhood. In the 1970s, astronomers discovered something extraordinary. Our galaxy, along with many others, was hurtling towards a hidden gravitational anomaly. They named it the Great Attractor. This cosmic enigma posed a perplexing question. What could be so massive that it disrupts the very fabric of the universe as expansion? Unveiling the mystery. To understand the mystery of the Great Attractor, we must first step back to the beginning, the very structure and motion of the universe itself. The key to this cosmic puzzle lies in understanding how the universe evolved from those primordial conditions. From the smallest fluctuations to the grand tapestry of galaxy clusters, each level of the cosmic hierarchy holds clues to the next. Seeds from the early universe. The origin of these flows lies in the very early universe. Tiny fluctuations in density. Imprinted in the cosmic microwave background, just 380,000 years after the Big Bang, served as seeds for future structure. Regions slightly denser than average grew under gravity, pulling in more matter, while underdense regions became cosmic voids. Over billions of years, these seeds grew into the vast structures we see today, the clusters, superclusters, and hidden attractor that steer the motion of galaxies, cosmic flows and peculiar velocities. As galaxies formed and evolved, their mutual gravitational interactions created intricate flows throughout the universe. Our Milky Way, situated within the local supercluster, finds itself influenced by these larger-scale flows, including the enigmatic Shapley Supercluster. This grand structure, spanning over 500 million light-years, contains hundreds of galaxy clusters and exerts a dominant gravitational force on surrounding regions. Its name comes from one of its most prominent members, the Shapley Cluster, also known as NGC 6397, a rich cluster of nearly 600 globular star clusters. To comprehend the impact of the Shapley Supercluster, imagine a cosmic whirlpool. At its center, the Shapley cluster acts like a vortex, drawing in nearby galaxies with its immense gravitational pull. Among these captive galaxies is Centaurus A, a unique member of the cluster. Unlike many of its cluster mates, Centaurus A is relatively close to us, making it a valuable target for study. Its proximity provides an opportunity to probe the nature of galaxy clusters and the forces that shape them. Furthermore, Centaurus A is a cannibal galaxy, one that is in the process of consuming a smaller galaxy. This adds another layer of complexity and intrigue to our understanding of galactic evolution. By studying Centaurus A, astronomers gain insights into the dynamical processes that occur within these massive cosmic structures. The Shapley Supercluster is a significant player in the grand cosmic ballet. Like a gravitational conductor, it influences the motion of galaxies across vast stretches of the universe. As we delve deeper into the Shapley Supercluster, we uncover a wealth of information about the nature of galaxy clusters and the dynamics of our universe. Each galaxy within this colossal structure contributes to the overall gravitational field, creating a complex web of interactions. By mapping the positions and velocities of these galaxies, astronomers piece together the history of the supercluster and its influence on our cosmic surroundings. At the heart of the mystery, our quest to understand the Great Attractor, takes us to the very heart of the Shapley Supercluster. Here we find not just a simple gravitational anomaly, but a region of profound complexity and intrigue. This enigmatic zone is marked by an unusual radio source known as the M82, M81 galaxy. These two galaxies, located near the center of the supercluster, emit an extraordinary amount of radio energy, creating a celestial beacon that has captured the attention of astronomers. Within this region, the gravitational forces are in a constant state of flux, giving rise to peculiar velocities that deviate from the expected Hubble flow. Galaxies within this zone are not merely receding from us due to the expansion of the universe, but they also experience the gravitational tug of the massive mass at the heart of the supercluster. This tugging effect causes some galaxies to move toward the center, while others recede. It's a cosmic dance of gravitational forces in motion. Furthermore, the M82, M81 galaxy, along with other radio-loud galaxies in the vicinity, emit jets of high-energy particles and radiation. These jets, extending thousands of light-years into space, carry a significant amount of energy and matter. As these jets interact with the intergalactic medium, they create shock waves and bubbles that extend far beyond the galaxies themselves. These structures serve as cosmic laboratories where high-energy phenomena occur, providing astronomers with valuable insights into the behavior of matter and energy under extreme conditions. Within this enigmatic region, the familiar laws of gravity seem to be challenged. Astronomers have discovered a peculiar galaxy known as the Cigar Galaxy, which defies expectations based on its location within the supercluster. Normally, one would expect the Cigar Galaxy to be influenced by the gravitational forces pulling it towards the center of the supercluster. Yet surprisingly, it appears to be relatively unaffected by these forces. This puzzling behavior suggests that the Cigar Galaxy may be surrounded by an invisible halo of dark matter. Dark matter, an elusive substance that makes up a significant portion of the universe's mass, is invisible to the naked eye. It neither emits nor interacts with ordinary matter or light. Yet its gravitational presence is felt throughout the cosmos. The Cigar Galaxy's apparent resistance to the gravitational pull of the supercluster could be explained by the presence of a substantial dark matter halo around it. This intriguing possibility highlights the role of dark matter in shaping the large-scale structure of the universe. By studying such anomalies, astronomers gain a deeper understanding of the distribution and influence of dark matter in our cosmic neighborhood. Yet the most tantalizing aspect of this region is the void, an enormous expanse of seemingly empty space that surrounds the supercluster. The Shapley void, with its diameter exceeding 100 million light-years, challenges our understanding of how matter is distributed in the universe. The near absence of galaxies within this vast region raises profound questions about the nature of cosmic structure formation. How can such a massive void exist? What role does it play in the evolution of the supercluster? Questions drive astronomers to explore the boundaries of the known and push the limits of our understanding. By studying the void, they seek to uncover the underlying mechanisms that govern the large-scale distribution of matter in the universe. As we continue to probe the depths of the Great Attractor, we encounter a vast array of celestial wonders that challenge our understanding and ignite our curiosity. From the colossal superclusters to the enigmatic voids, each discovery brings us closer to unraveling the mysteries that lie at the heart of our cosmic neighborhood. The Great Attractor, once a perplexing anomaly, is now revealing its secrets, inviting us to explore the intricate workings of our universe. There's a monster lurking in our cosmic backyard. We can't see it, but we know it's there because of what it does. It warps the very fabric of space-time. It affects how other objects move through the universe. Just figuring out how to locate it has fundamentally changed our understanding of cosmology. So far, astrophysicists have discovered two such beasts, each more massive than the last. Together, they make up a great cosmic tugboat that is steering our Milky Way through space. They call it the Great Attractor. Our sun is traveling around the center of the Milky Way at roughly 250 kilometers per second. And like all points in our galaxy, it is speeding up as the universe expands. That means the sun is moving away from most of the other galaxies in the universe. At least that's what we would expect if gravity didn't play a role on the largest scales. But in the 1970s, researchers started noticing that something was wrong. Galaxies in the nearby universe weren't receding from us at the rate we'd expect. Some of them were moving towards us instead. In 1978, An international team of astronomers, led by Roger Penrose at the University of Cambridge, mapped the velocities of 48 bright galaxies and found that while most of them were receding from us, 6 were moving towards the constellation of Norma, which lies in the southern celestial hemisphere. And in 1981, another group of astronomers confirmed the results with a larger sample of galaxies. But there was a problem. It was impossible to actually see anything in that area. The region was behind the so-called zone of avoidance, a swath of sky that is blocked by dust clouds and stars in our galaxy. We don't see through it because light from distant stars has to travel through that dust, and it just gets absorbed. So when astronomers looked into the region of Norma, they could see basically nothing. But that didn't stop them from making inferences about what was going on there. These astronomers knew that all of those galaxies had to be grouped together in one way or another. Otherwise, they wouldn't be falling towards the same point in the sky. And since we couldn't see any individual galaxies in that area, that meant they had to be grouped together in a huge cluster, so massive that its gravity could warp the space-time around it. It was an exciting discovery. Till then, astronomers had assumed that space was flat on the largest scales, meaning that gravity wouldn't cause noticeable distortions anywhere in the universe. But if there was a giant cluster of galaxies lurking behind the zone of avoidance, then gravity really did have an effect on large scales. And if that was the case, then our own sun and solar system might not be moving purely away from other galaxies either. Maybe we were being pulled towards that invisible cluster. The idea was controversial, though, because astronomers disagreed about how fast the galaxies in that region were actually moving. If the recession velocities were smaller than expected, that would mean that gravity really was affecting our motion. But if they were just as expected, then space was still flat, and there was no monster in our backyard. Eventually, more data came in, and it turned out that the true velocities of the galaxies were indeed lower than expected. That meant that our sun is moving towards the monster, and it made the search for that monster a priority for astronomers. But it wasn't easy. To find it, they needed to peer into even more of the zones of avoidance. That required new telescopes and new technology. In the meantime, some researchers tried to take advantage of the fact that the monster would distort our view of objects behind it, allowing them to infer its location by looking for gravitational lensing. Fortunately, those efforts failed to reach a conclusion. But eventually, in the 1990s, new X-ray and infrared telescopes were able to actually see the monster, or at least the center of it. They found a huge cluster of galaxies called Able 3627. It is massive, contains thousands of galaxies, and has a huge reservoir of dark matter in its halo. And it does seem to be attracting the surrounding galaxies. But it isn't massive enough to explain why our solar system is falling towards it. That means the monster was actually bigger than astronomers originally thought, and it was time to start looking again. This time the focus was a little narrower. Astronomers knew to look for something called the peculiar velocity of galaxies. This is the velocity of a galaxy relative to the speed that it would have if it were only affected by the expansion of the universe. With that in mind, several teams of astronomers embarked on ambitious projects to map the positions and velocities of thousands of galaxies throughout the sky. The largest of these projects was the 2DF Galaxy Redshift Survey, which measured the redshift of nearly 200,000 galaxies. These redshifts were used to calculate their distances and therefore their velocities relative to our own. And when they mapped those velocities, it became clear that the monster was far bigger than just the Norma cluster. Our sun isn't falling just towards that cluster, towards a huge supercluster of galaxies located 650 million light-years away in the constellation of Centaurus. This supercluster is now known as the Shapley Supercluster, and it is one of the most massive structures in the nearby universe. It contains over 8,000 galaxies bound together by their gravity, including the original Norma cluster. It is so massive that it does affect our motion. According to some estimates, it accounts for over half of the peculiar velocity of the solar system. But that doesn't tell us anything about the shape of the structure. Could it be spherical, or perhaps cylindrical? To find out, astronomers used the peculiar velocities of the galaxies to model the gravitational field in the region.
Ow.
The best fit model was a single massive sphere. But that doesn't mean that the Shapley Supercluster is actually a sphere. It's more likely that the model represents the gravitational effect of an infinite number of small structures within the supercluster that collectively act like a single mass. These structures are the filaments and sheets of the cosmic web. And the Shapley Supercluster simply marks the center of one of these filaments. But there's one thing that is hard to understand about the Shapley Supercluster. The galaxies within it aren't actually falling towards its center. That's because our Milky Way isn't the only thing that's moving. All of the galaxies within the supercluster are also feeling the pull of the cosmic web. So they being pulled in different directions, and they not all ending up in the same place. So while the Shapley Supercluster does explain most of the motion of the solar system, it isn't the whole story. There is another factor at play, one that astronomers only discovered in 2017, like the Shapley Supercluster. It wasn't detected by looking at the things that are attracting our solar system, but by looking at what's repelling it. See, gravity doesn't just pull objects towards each other, it also leaves behind regions where matter is sparse. So, while the Shapley Supercluster is attracting our solar system towards its center, there is also a part of space behind it that is effectively pushing us away. Researchers call this feature the Dipole Repeller. Like the Shapley Supercluster, it lies in the zone of avoidance. Unlike that structure, we've never been able to see any galaxies inside of it. That's because it isn't a cluster, but a void, a huge empty region of space. If the Shapley Supercluster is a tug, the dipole repellent is a sail, and it is big. The void extends for more than 600 million light-years, and it is about 3 times wider than the Shapley Supercluster. While the cluster pulls us towards it at around 60 kilometers per second, the void repels us at around 30 kilometers per second. The dipole repellent is less massive than the Shapley Supercluster, so by itself it wouldn't be able to change the course of our galactic cruise. But combined with the pull of the cluster, the repulsion of the void makes up an incredibly powerful gravitational tugboat. Together, they steer our Milky Way along a path that is warped relative to the smooth fabric of space-time. A new study says they've figured out exactly how much dark matter there is in the Great Attractor, the huge cluster of galaxies which our Milky Way is falling towards. Let's have a look. This image shows you the constellation of Centaurus, the one with the 2 guys fighting with each other. And yes, I made that up. You can see them, right? It's a guy in the back about to stab the other with a spear. And no, I didn't steal that from your copy of Harry Potter. Here's the original. I really wish I could draw. Anyway, this picture has become famous in astronomy because it was taken with the European Southern Observatory SVLT survey telescope. And the dark patches in the foreground are not empty. They are huge clouds of dust, like several times the size of our solar system. And you can already see some of the features that make studying this region so difficult. In the late 1970s, astronomers noticed that something funny is going on with galaxies in this region. They seem to be moving towards a spot near the Antares constellation. That something funny is now called the Great Attractor. Today we know that the Great Attractor isn't a thing. It's a region of space. Our Milky Way is currently cruising through this area at about 2.2 million kilometers per hour. It's not us. Other galaxies are affected too. Most of the galaxies in the local supercluster are also falling towards this region. We don't know exactly where the center of this attractor is, but somewhere in this direction, but not necessarily in this plane. So in this video, I'll sometimes show you the circle and sometimes a cross-section through it. But keep in mind, both are just different ways to visualize the same thing. It's a little bit like when someone asks you, where do you live? You might say, I live in Berlin, and that's true. But if you wanted to find your house, you need to tell them more than just that you live in a city because there are many houses in Berlin. Astronomers had hoped that by now we'd know where this attractor is, well, partly because it's been almost half a century since we discovered that something funny is going on down there. But progress has been slow. First of all, because the Great Attractor lies in a region that's very difficult to observe. It's in the plane of the Milky Way, which means that the Earth's atmosphere blurs the view. Also, the bright foreground stars of the Milky Way make it hard to observe faint background galaxies. So what's down there? Is it some kind of anomaly in the universe? A black hole, perhaps? Something strange? Well, it turns out that the Great Attractor is just a collection of normal galaxies, just lying on our way. The reason why they attract us is that they contain a lot of mass. Stars and gas, whatever makes up these galaxies, they all have a gravitational pull. And together they create a sort of gravitational well. The more mass, the deeper the well. And the interesting question is, how deep is this well? Does it have some particular shape? How much is it pulling things around? This is what astronomers want to know. Now, in principle, you can measure how deep the potential well of a group of galaxies is. If you know the velocity of the galaxies that are inside the group, you can use that to calculate how much mass there must be. This method is called the dynamical mass, and it doesn't just work for groups of galaxies, but also for clusters and superclusters. But there's a problem. For one thing, these calculations require that you know whether the galaxies all move around in a common way or whether they move independently. For the galaxies in a cluster, it's generally the first case. But for a structure as big as the Great Attractor, it's not clear that all the galaxies inside it belong together. Some might just happen to be close by. Then again, most appear to be indeed bound together and moving in a common way. That makes it plausible that it's one thing, but it's not proof. This is why it's been so difficult to come up with a consistent model for the mass of the entire structure. Different groups used different assumptions about how to count the mass, and that led to wildly different numbers. Some studies say the mass is a few trillion times that of the Sun. Others said it's 30 trillion. Still others say it's as much as 100 trillion. Just to give you an idea, the entire Milky Way only contains about 100 trillion stars. Yes! So it's quite possible that the Great Attractor is more massive than our galaxy. That's why it pulls us towards it. Now you might ask, wait, this sounds like the issue with the measurements comes from not knowing how much mass the galaxies in the region have, and you'd be right. But unfortunately, there's another problem. It's that the simple formula I gave you earlier doesn't just contain the mass of the galaxies. It also contains the mass of something we can't see, dark matter. The issue with dark matter is that it doesn't interact with anything except gravity. So it's impossible to measure it directly. All we can do is infer its presence indirectly from its gravitational pull. Since dark matter doesn't emit light, it's basically invisible. In fact, astronomers call it dark matter because it doesn't interact with anything, hence dark. They just infer its presence from its gravitational pull. They have good reasons to think that it exists. But the issue is that the amount of dark matter in any of these structures depends strongly on the model. In the new paper, the authors say they have solved this problem. They determined the amount of dark matter in the Great Attractor by using data from the Wiggles project. That's a survey that measured how the gravitational lensing of background galaxies changes over time. They combined that with a model for how dark matter should contribute to the gravitational lensing, and then they fit the model to the data. They say that this gives them a much better determination of the amount of dark matter in the Great Attractor, and it's smaller than in previous studies. I'm going to be honest, I think this is a little bit boring. I mean, I'm sure it's correct. That sounds correct. But this just goes to show you what I dislike about so much research in fundamental physics. It's not that we have little understanding of nature, it's that we've completely lost the overview. We have so much data, but it's also technical. There are dozens of different ways to extract information from the cosmic microwave background, and every group does it a little differently. And there are dozens of different ways to analyze gravitational lensing, and every group does it a little differently. And then each of these analyses requires a model for dark matter. And depending on the model, you get different results. And everyone does the models a little differently. Then the results are often mutually contradictory. And everyone keeps fitting new data to their favorite model, and then they all pat each other on the shoulder and declare that the results agree with each other within the error bars. And meanwhile, the error bars are so large that you can fit a cat through them, and here's my bet. 5 years from now, this result will be forgotten. It'll turn out that the data doesn't quite fit the model, or the model didn't quite fit the data, or the data analysis was wrong, the data was misinterpreted, or the model was a little off, or maybe the data wasn't real. Who knows? The moral of the story is, if you want to understand the world, don't just focus on memorizing lots and lots of data. It's also important to have an overview. Don't forget the overview. We live in a dynamic universe, one that is always changing, expanding, and evolving. While we might feel stationary on our little blue planet, our place in the grand scheme of the cosmos is actually quite the opposite.
Ow!
Earth is in constant motion, hurtling through space at mind-boggling speeds. So join me on a journey as we uncover the astonishing reality of our world and learn just how fast Earth is really moving. The Earth's movement through space and time. Let's start with the basics. Our planet is not just flying around randomly in space. It is on a well-defined path around the Sun, completing one orbit every 365.25 days. During this journey, the Earth experiences different seasons due to the tilt of its axis relative to the Sun. But it's not just the Sun, it's that the Earth revolves around. Our solar system, with the Earth and all the planets, is also in motion around a central point in the Milky Way galaxy. The Sun, along with its planetary retinue, is whizzing through space at approximately 828 kilometers per second. This rapid movement carries us on a path that takes us around the galactic core once every 230 million years. But wait, there's more. The Milky Way galaxy is not an isolated island in the universe. It is part of a grander structure known as the Local Group, a cluster of about 50 galaxies, including Andromeda, which is our closest major galactic neighbor. The Local Group is not static, it is on the move, hurtling towards the Great Attractor at a speed of about 2.2 million kilometers per second. To put that in perspective, that's about 8 million times faster than the fastest man-made object, the Great Attractor, a gravitational tapestry. Now let's focus on the destination of this cosmic journey, the Great Attractor. The Great Attractor isn't a single star or planet. It's a vast region of space, teeming with hundreds of galaxies. At first, astronomers were puzzled by the strange gravitational pull they felt coming from this area. The name Great Attractor was given because it was the center of a gravitational field so strong that it seemed to be attracting everything around it. However, as we delve deeper into the mysteries of the Great Attractor, we find a fascinating story of gravity, mass, and motion. As of now, the Great Attractor remains shrouded in mystery, hidden behind a cosmic veil of dust and gas. This celestial fog prevents us from seeing very far into the depths of the Great Attractor. But astronomers are not deterred. Using powerful telescopes, both on Earth and in space, they've managed to peer through this cosmic haze, revealing a captivating sight. What they found is a bustling hub of activity with countless stars, including many blue and bright young stars being born. There's also evidence of supernovas, the spectacular explosions that mark the end of a star's life, suggesting a dynamic and active region of space. Now let's talk about speed. The Earth is not just orbiting the Sun and whizzing around the galaxy. It is also on a cosmic highway of sorts, traveling at incredible speeds toward the Great Attractor. The Earth's speed on this journey is awe-inspiring, about 299,792 kilometers per second. To put that in perspective, that's about 1.1 million times faster than the speed of sound. If you were to travel at this speed, you could circle the Earth's equator in just under 0.01 seconds, completing a lap before your next blink. Earth's motion and the Shapley Supercluster. As we continue our journey, we encounter another cosmic landmark, the Shapley Supercluster. The Shapley Supercluster is a vast assembly of galaxies, including the large and small Magellanic Clouds, which are satellite galaxies of the Milky Way. These galaxies, along with many others, are grouped within the Local Supercluster, a larger structure that encompasses the Local Group and the Shapley Supercluster. While not technically part of our Local Group, the Shapley Supercluster is close enough to influence our motion and is sometimes included in discussions of our galactic neighborhood. So how fast is Earth moving relative to the Shapley Supercluster? Here's where things get even more intriguing, because the Shapley Supercluster is not just a passive collection of galaxies. It too is in motion. It is moving towards the Great Attractor at a speed of roughly 185 kilometers per second. Now consider the Earth's motion relative to the Shapley Supercluster. Add the speed of the Earth around the Sun's movement in the Milky Way, and the Milky Way's journey towards the Great Attractor, and you have a total speed of around 301,000 kilometers per second. That's about 1.3 million times the speed of sound. Our place in the grand scheme of things. You might be wondering, why should we care about these distant galaxies and their effect on Earth? After all, they are incredibly far away and seem almost otherworldly. However, understanding our motion relative to these structures gives us a deeper appreciation of our place in the universe and helps us understand the workings of the cosmos on a grand scale. By studying the motion of galaxies and superclusters, astronomers can learn about the distribution of matter in the universe, the nature of dark energy, and the evolution of galaxies over time. The more we understand about the motion of objects in space, the better we can understand the forces that drive them. What lies beyond the veil? The Great Attractor and the Shapley Supercluster represent just a small part of the universe that we have explored. there are countless other structures out there waiting to be discovered. Astronomers are constantly making new discoveries about the universe and our place in it. And with new telescopes and space missions, we are sure to learn even more in the future. The James Webb Space Telescope, for instance, is expected to revolutionize our understanding of the early universe and the formation of galaxies. Earth's motion in the Laniakea Supercluster. Now let's zoom out even further. The Laniakea Supercluster is a vast expanse of space that contains hundreds of thousands of galaxies, including the Milky Way and the Andromeda Galaxy. It is the largest known structure in the observable universe and provides a unique opportunity to study the large-scale structure of the cosmos. The galaxies within the Laniakea Supercluster are not evenly distributed, but instead form a network of filaments and clusters. Our Milky Way is located near the edge of this supercluster, and its motion relative to the rest of the cluster is of great interest to astronomers. Using data from the Hubble Space Telescope, astronomers have been able to map the motion of galaxies within the Laniakea Supercluster. They found that our Milky Way is moving at a speed of about 1.3 million kilometers per second relative to the center of the supercluster. This means that our galaxy is not just drifting through space, but is actively being pulled towards the center of the Laniakea Supercluster. Cosmic tapestry. Our journey through the vastness of space has revealed an astonishing truth. Earth is not merely a stationary observer, but an active participant in a grand cosmic ballet. From its daily rotation on its axis to its yearly revolution around the sun, our planet is in constant motion. And when we look beyond our solar system, the picture becomes even more dynamic. Our solar system, along with the Earth, is hurtling through the Milky Way galaxy, and the galaxy itself is streaming towards the Great Attractor within the Laniakea Supercluster. Furthermore, we've explored the enigmatic Great Attractor, cosmic tapestry woven with threads of gravity, mass, and motion. While the Great Attractor remains shrouded in mystery, its allure lies in the promise of unraveling the secrets of our universe's evolution. As we continue to probe the depths of space, we discover that our Earth is not just a small dot in the grand scheme of things, but a traveler on a never-ending cosmic adventure. The Earth is a traveler on a never-ending cosmic adventure. In this grand journey, we are carried along by the gravitational pull of distant galaxies, forever bound to the rhythm of the universe. With every new discovery, we deepen our understanding of our place in the cosmos. And as we gaze up at the stars, we are reminded that the Earth is not just a home, but a spaceship carrying us through the boundless expanse of space and time. In the grand expanse of the universe, there are few mysteries as compelling as the one that has captivated astronomers for decades. Behind the curtain of stars in our own Milky Way lies a cosmic enigma known as the Great Attractor. Like a silent giant, it has exerted an irresistible gravitational force on scientists, driving them to uncover its secrets. Join me on a journey through time and space as we explore the fascinating story of the Great Attractor and its enduring impact on our quest to understand the cosmos. The Great Attractor, a name that echoes the awe and intrigue surrounding this celestial enigma. Its existence was not a mere accident of discovery, but a testament to the relentless pursuit of knowledge that defines humanity's greatest scientific endeavors. Long before astronomers laid eyes on this cosmic marvel, its presence was subtly hinted at through peculiar velocities. As they meticulously charted the movement of galaxies, they noticed that some celestial neighbors were not receding as expected. They seemed to be approaching us, as if drawn by an invisible force. Could there be something lurking behind the curtain of stars, exerting a gravitational influence so strong it defied the very laws of the universe? This perplexing observation planted the seeds of curiosity that would eventually lead to the revelation of the Great Attractor in the late 1960s and early 1970s. As technology advanced, the pieces of the cosmic puzzle began to fall into place. Vera Rubin and her colleagues made groundbreaking measurements of galaxy rotation rates, providing crucial insights into the nature of dark matter. Their findings suggested that the visible matter in galaxies accounted for only a fraction of their mass, with the majority residing in a mysterious invisible form known as dark matter. This breakthrough discovery not only revolutionized our understanding of astrophysics, but also provided a potential explanation for the peculiar velocities observed in galaxies. Dark matter, with its elusive nature and gravitational influence, could be the key to unraveling the enigma of the Great Attractor. As the years went by, the quest to understand the Great Attractor became more urgent. Scientists yearned to see beyond the veil of stars that obscured our view, driven by an insatiable curiosity to know what lay hidden in the uncharted territories of our universe. However, the path to discovery was fraught with challenges. The Great Attractor, shrouded in mystery, posed an observational obstacle that threatened to impede progress. How could astronomers hope to understand something they could not see? Undeterred, they turned to infrared radiation, hoping it would be their ticket to unlocking the secrets of the Great Attractor. In the 1980s, the Infrared Astronomical Satellite, or IRAs, embarked on a mission to map the cosmos in infrared light. Its keen eye pierced through clouds of dust and gas, revealing a wealth of previously unseen celestial objects. And then, much to their astonishment, the data revealed a cluster of galaxies in the constellation of Coma Berenices, known as the Coma Cluster. It was a significant discovery, not just because it unveiled a hidden cluster of galaxies, but because it offered a potential solution to the problem of the peculiar velocities. Could this massive concentration of galaxies be the source of the gravitational pull that had puzzled astronomers for years? The Coma Cluster became a focal point of investigation, and as studies deepened, the picture became clearer. It was not a single cluster, but a vast collection of galaxy clusters forming a supercluster. This monumental structure, spanning over 500 million light-years, was later named the local supercluster in recognition of its proximity to our own galactic home. As the 20th century drew to a close, our understanding of the universe underwent a profound transformation. Thanks to the efforts of countless scientists, the Great Attractor was no longer a distant enigma. It had become a tangible part of our cosmic landscape. With each passing year, the veil of obscurity that had shrouded the Great Attractor for centuries was lifted, revealing a tapestry of galaxies and clusters that defied imagination. The ongoing saga of discovery continues to captivate astronomers today. As technology advances, our view of the Great Attractor becomes even more precise, unveiling intricate details and shedding new light on its formation and evolution. The study of the Great Attractor has not been a solitary endeavor. It has been a testament to the power of collaboration and the relentless pursuit of knowledge that drives humanity forward. In the early days, pioneers like Fred Hoyle and William Herschel laid the foundation by charting the night sky and classifying celestial objects. Their work paved the way for those who followed, each adding a new piece to the cosmic jigsaw puzzle. Then came the era of space exploration. Telescopes like Hubble, Spitzer, and Chandra revolutionized our perspective, peering deep into the cosmos and capturing images of never-before-seen wonders. They unveiled the birthplaces of stars, the remnants of exploded stars, and the dance of galaxies in the grand ballet of the universe. As we look back on the incredible journey of discovery that has brought us to this point, we realize that the Great Attractor is more than just a cosmic phenomenon. It is a symbol of human curiosity, ingenuity, and the relentless pursuit of knowledge. From the earliest astronomers who gazed at the stars and wondered about the nature of the universe to the modern day scientists who use sophisticated instruments to unlock its secrets, our fascination with the cosmos has never waned. The story of the Great Attractor is a story of human evolution. It reflects our insatiable desire to understand the world around us and to push the boundaries of what we know. It reminds us that even in the face of challenges and setbacks, the pursuit of knowledge and the spirit of discovery will always guide us forward. So let us continue to explore, to question, and to marvel at the wonders of the universe. For in doing so, we are not only expanding our understanding of the cosmos, but also expanding our place within it. As we stand on the shoulders of giants, let us embrace the spirit of collaboration that has brought us so far. Let us work together, sharing our knowledge and resources to unravel the mysteries that still lie ahead. For in unity we find strength, wisdom, and the power to explore even the most challenging frontiers. As we reflect on the incredible journey of discovery that has brought us to this point, we must also acknowledge the immense challenges that lie ahead. The Great Attractor, while partially unveiled, still holds many secrets that we have yet to uncover. Its true nature, its impact on the evolution of the universe, and its role in shaping the galaxies around us remain shrouded in mystery. Yet these challenges also present us with an opportunity to push the boundaries of human knowledge and to explore the unknown with renewed vigor. As technology advances, we stand on the cusp of a new era of discovery. With the launch of the James Webb Space Telescope, we have opened a new window to the universe, poised to capture infrared light and unveil the hidden wonders of the cosmos. This technological marvel will enable us to peer deep into the hearts of galaxies, to witness the birth of stars and to explore distant worlds that were previously beyond our reach. But it is not just about the tools we use. It is about the brilliance of the human mind, our capacity to innovate, and our determination to explore the uncharted territories of the universe. Through sheer ingenuity, we have developed new techniques and approaches that allow us to analyze data, model complex phenomena, and probe the deepest mysteries of the cosmos. As we venture further into the unknown, we must also embrace the spirit of adventure that has always driven humanity forward. The Great Attractor beckons us to explore its enigmatic depths, its promising revelations that will redefine our understanding of the universe. Are you ready to join this cosmic odyssey? Are you eager to discover what lies hidden behind the curtain of stars? The Great Attractor awaits, and with it, a universe of wonders. So let your curiosity guide you, your imagination soar, and your spirit of discovery ignite. For together, we can unlock the secrets of the Great Attractor and unveil the hidden harmonies of the cosmos. The story of the Great Attractor does not end with discovery. It opens a new chapter. What does our motion toward it mean for the future of the Milky Way, the local group, and the universe as a whole? And what deeper truths does this mystery point to about the nature of reality itself? Let's start by zooming out to get a feel for where we're heading, the immediate future. Galactic drift on timescales of tens to hundreds of millions of years, our galaxy and its neighbors will continue drifting toward the Great Attractor region. This motion will not be catastrophic or violent on a human scale. Instead, it's part of the natural cosmic ballet of galaxies, moving along the filaments of the cosmic web, merging, clustering, and flowing under the pull of gravity. Eventually, the local group itself will merge with the Virgo cluster, and over time, with larger structures in the Laniakea Supercluster. The Great Attractor is simply one waypoint in this long gravitational journey. But this drift is not without consequence. One of the most immediate effects will be felt in our own backyard. The large and small Magellanic Clouds, dwarf galaxies orbiting the Milky Way, will eventually merge with us as a result of our collective motion toward the Great Attractor. These events aren't on the order of the heat death of the universe, but on galactic timescales, they're relatively close. By understanding these processes, we gain insight into how galaxies evolve, change, and interact. However, there's a counterforce to all this, one that could one day change the course of our galactic future: dark energy. While dark energy doesn't have a direct effect on the motion of objects within our cosmic neighborhood, it does affect the expansion of the universe. And on the largest scales, that can matter. The role of dark energy, the flow that slows as the universe expands. The force of dark energy becomes more significant. Not that dark energy gets stronger, it's that as the universe expands, the influence of gravity weakens. Over billions of years, this shift in balance could cause the expansion of the universe to overcome the pull of the Great Attractor. At that point, the Milky Way and other nearby galaxies would effectively be freed from their collective fall. But don't expect any sudden changes in your lifetime. Estimates vary, but some studies suggest that we woe and feel the effects of this shift for at least 100 billion years. Even then, the transition wouldn't happen overnight. It'd be a slow drift that would take millions of years to unfold. Nevertheless, if this scenario plays out, it would be a monumental event in the history of our galaxy, one that would sever our ties to many of our galactic neighbors. In fact, this is already happening to a small degree. The Pavonia region, located behind the constellation of Pavo, shows signs of being ejected from the local supercluster. It's too far away for us to study in detail, but it seems to be moving away from us faster than the speed required to escape the gravitational pull of the Great Attractor. Some scientists speculate that the Pavonis might have been a rogue galaxy captured by the supercluster at some point, and now it's finally escaping. Or it could be a sign that the gravitational grip of the Great Attractor is already weakening due to the influence of dark energy. More observations and research are needed to understand this phenomenon fully, but it serves as a reminder that the dynamics of our cosmic neighborhood are always evolving. the cosmic horizon losing the evidence, but time is relentless. And over billions of years, the story of the Great Attractor could fade from the cosmic record. As the universe expands, the light from distant galaxies will stretch, shifting them from the visible spectrum into longer, invisible wavelengths. This means that galaxies beyond a certain distance will become impossible to detect, disappearing from view as they recede into the darkness. This point of no return is known as the cosmic horizon. What's more, the evidence of our cosmic motion, such as the dipole and the cosmic microwave background radiation, will also vanish from our perspective as the universe expands. Future astronomers born into a universe without this dipole may not even know it existed. They might assume that the universe is static and empty. It's unaware that we once lived in an era when the cosmos was filled with gravitational flows and large-scale structures. For us today, the Great Attractor and its surrounding flows are within our observable universe. However, the lack of evidence for them in the distant future highlights the idea that our position in cosmic history is unique. We are privileged to live in an era when the structure and dynamics of the universe are readily observable. This realization adds a layer of urgency to our scientific endeavors. We must document and understand what we see today, knowing that future generations may not have the same opportunity. The philosophical question, where is here? The Great Attractor forces us to rethink what it means to have a cosmic address. For most of human history, we assumed that Earth was the center of everything. Then we learned that the Sun, not Earth, is the center of our solar system. With the discovery of the solar system's motion around the galaxy, Earth lost its central status. And now, as we explore the motions of our galaxy within the local group and the Laniakea Supercluster, the idea of a fixed cosmic address dissolves entirely. We are not merely at a specific location, we are on a journey. Our cosmic home is not a place, but a process. We are here as part of an ongoing flow, carried along invisible currents of matter and energy, toward destinations we can barely glimpse. This perspective challenges our intuitive understanding of space and time, urging us to think of our universe as a living, breathing entity rather than a static stage. In this sense, the Great Attractor is more than a gravitational anomaly. It's a symbol of our journey, our constant movement through space and time, our ceaseless search for what lies ahead, and our determination to uncover the unseen. The scientific frontiers. Unfinished questions despite recent progress. Many questions about the Great Attractor remain unanswered. Scientists are working to map the gravitational flows of the cosmos more precisely. But the full story of our motion is still being written. Here are some of the frontiers that scientists are eager to cross. What is the exact mass distribution of the Great Attractor region? Observations suggest that there's a massive concentration of galaxies around 200 million light-years away. But the details of its structure are still shrouded in mystery. Improved infrared surveys and deep radio surveys using instruments like the Square Kilometer Array could shed more light on this hidden mass. How much of our motion is due to Shapley, how much to local structures, and how much to voids like the Dipole Repeller? Understanding the relative influence of these features would provide a clearer picture of the forces shaping our cosmic journey. Advanced simulations of cosmic structure combined with detailed observations could help untangle this web of influences. What role does dark matter play in organizing these flows? Computer models suggest that dark matter is crucial for the existence of the cosmic web and the large-scale structures we observe today. Further study of the distribution of galaxies and the influence of dark matter could reveal how these structures evolved over time. These questions are just the beginning. As science advances, new puzzles will undoubtedly emerge, keeping the Great Attractor a vibrant area of research for generations to come. The human place. Riding the current on a human level, the Great Attractor reminds us that we are not fixed. Our planet, our solar system, our galaxy, everything is moving. We are passengers in a flow that began with the Big Bang, carried along invisible filaments of matter and energy, toward destinations we can barely glimpse. This realization puts our existence in a broader context. The actions and decisions we make are not just about our individual lives or the fate of our species. They are part of a much larger story, a cosmic narrative that spans billions of years and encompasses trillions of stars and galaxies. The Great Attractor challenges us to adopt a wider perspective, one that acknowledges our place in the grand scheme of the universe, yet at the same time it offers us hope. If our cosmic journey has brought us to where we are today, capable of exploring the depths of space and unraveling the secrets of the cosmos, what else might it have in store for us? Perhaps the challenges we face today are stepping stones on a path that leads to even greater discoveries and understanding. Maybe the Great Attractor is guiding us, subtly urging us to push the boundaries of human knowledge and reach for the stars. Final reflection: the mystery that endures the Great Attractor will continue to be studied, debated, and redefined. It may turn out to be less a single object than a convergence of many structures. It may eventually fade beyond the horizon. But the act of searching for it has already changed how we see the universe. It taught us that galaxies are not islands, but parts of vast rivers of matter flowing through the cosmic web. It showed us that voids are as important as clusters in shaping motion. And it revealed that our cosmic story is not static, but dynamic, a story of motion, attraction, and expansion. In the end, the Great Attractor is both real and symbolic. Real in the sense of a measurable gravitational pull. Symbolic in the way it reminds us that even the universe itself has hidden depths, waiting to be mapped. And as we continue to trace these hidden currents, we may discover that the universe is not just expanding, it is guiding us subtly toward understanding our place in the grand cosmic flow.